where we're measuring uranium, thorium, lead, and then as George mentioned, we're measuring mercury for interferences. And we spent the afternoon talking about lutetium, hafnium. We also need to measure ytterbium in there. Now we're kind of jumping into the big bad world of trace and rare earth element chemistry. And I say big bad world because there's just so much to work with, right? You're looking at your periodic table, and at least in our lab, we measure 23 trace and rare earth elements when we do these kind of analyses. So the types of data and the types of questions that you can start to ask are kind of insane. So the pink squares here are highlighting our trace elements. This black box down here, of course, the rare earth elements, the lanthanide series. And so we're going to spend the rest of this day talking about kind of what are some of the applications that you can start to do with this. And again, I've done some of these, but I am by no means an expert on all of them. So I'm just going to show you some examples and work through those together. And then I'd refer you to the papers for additional information. Okay, so coming back to kind of the basics of zircon and where these things are going. So again, zircon is a tetragonal orthosilicate. We have zirconium living in the 8-fold site, silicon living in the 4-fold site. So things like hafnium, thorium, uranium substitute into the zirconium site. Things like titanium, which has a smaller ionic radius, substitute into the silicon site. And this exchange process actually turns out to be a temperature dependent process, which is really neat because it gives us a thermometer within the zircon system. So we'll come back to that later. So most of our rare earth elements are 3+ cations, the 2 exceptions there, of course, being cerium and europium, which can exist in other valent states. And so those 3+ cations for rare earth elements, along with yttrium, which is also a 3+ cation, they need a coupled substitution to get into the crystal lattice. So this often occurs with phosphorus 5+, so that you get charge balance where you have 3+ plus 5+ is the same as 4 + 4, so 8+. And so that often substitutes for the zirconium and silicon. So the heavy rare earth elements tend to fit a lot better into this crystal lattice. Their ionic radius is a lot more compatible. So we have pretty readily have substitute in the heavy rare earths, but the light rare earths substitute in less so. And that's just a function of their ionic radius, going back to basic Goldschmidt's rules. So here, man, we've just been giving Belousova all the love today. So here's another figure from Elena Belousova. This is from her classic 2002 paper where she did something quite similar with zircon trace and rare earth elements. And she basically analyzed all of these zircon trace and rare earth elements from a variety of different rock types and started to characterize some key fingerprints for what different concentrations might look like in different zircon types. But as we kind of suggested before, they always have relatively high thorium, high uranium, and high hafnium in their structure, not lutetium. And so these are normalized to chondrite, and you can kind of see some of the other things that incorporate in, typically in this kind of 0.1 to 1,000 ppm range. Okay, so this is a really fun diagram. I think this originally came from Brad Hacker and Kyler Clark in a previous short course. So if you're looking at a typical crustal zircon, it would look something like this in its rare earth element pattern. So again, depleted in the light rare earth elements, enriched in the heavies. But if you're getting cogenetic growth of garnet loves heavy rare earth elements. So it's going to suck up all those heavies, and zircon's going to pay the price. So you might get depletion in those heavy rare earth elements. So this type of kind of like intuition is how you might start thinking about these systems. So the zircon chemistry is going to be a function of of what rock type it's coming out of, kind of the work that we saw by Elena Belousova, by what minerals are cogenetically crystallizing with zircon, and things like temperature. Okay, so we can do the same game with plagioclase, only this time we're gonna break down our plage. Plage has a very strong europium anomaly. And so if we're breaking down plage, zircon's gonna incorporate that kind of europium anomaly. Okay, so something that we talked about a little bit early on in this course was limits of detection. And of course, that's not so important for our uranium and lead. We have typically relatively high concentrations, but trace elements are in trace abundances. And so we need to be concerned about whether or not our analytical technique is capable of measuring those. So here's a bunch of the different trace and rare earth elements. And this red line here at roughly 0.1 ppm corresponds to kind of our typical limit of detection for laser ablation, ICP mass spectrometry. Note that lanthanum and praseodymium, two of the elements that we'd really love to be good at quantifying because they're good at things like tracing crustal thickness through time. We have a bit more trouble quantifying, but we think that we do a pretty good job on our system based on our standard bracketing. So how can you measure these things? We've seen a lot of these names before, so we can easily do it via laser ablation inductively coupled plasma mass spectrometry like we have in our lab. You can either do this on a split stream setup where you're ablating one zircon, you're funneling half of your signal into a mass spectrometer that's reading off the uranium lead age, and another mass spectrometer that's separately measuring these trace and rare earth elements. What we do at Arizona Lasercron is we measure it all on one machine. We measure it on our element 2 single collector mass spectrometer, which basically cycles through masses through time and allows for simultaneous acquisition. And we seem to do pretty well with the uncertainties. So we think we're around 5–15% for the uncertainties on those trace and rare earth elements. So you can also do it via solution ICP mass spectrometry. Of course, you probably get more precise trace and rare earth element compositions, but then you have to dissolve your zircons. So that's a whole analytical challenge. You can do it on the SIMS where you get great spatial resolution, but of course the throughput is much slower as we talked about before. One of the things that you might be interested in if you've already dated a bunch of zircons is you can go back in with an electron microprobe. The limits of detection aren't quite as low as they are lower than, we cannot detect things as well on an electron microprobe, so you might suffer that way. But they're relatively cheap to use, so they're much cheaper than doing these analyses via laser ablation. And these analyses can't be conducted on an SEM. So kind of what we've done before, going through some of the standards that we use and kind of some of the best practices here. So George mentioned this before, we really like to use what we call matrix match standards. So these are standards that are made out of the same material as the material that we're analyzing. So in this case, we're analyzing zircon, so we want zircon standards. We used to use these two, 91500 and MAD 559. These were kind of community-based standards. And then we got to like the second to last grain of MAD 559. And so we've switched over to some in-house standards. So now we're using SLF and FC. And then we use NIST as kind of like something to monitor through time. We need to make sure that a lot of these trace elements have interferences. So if you're measuring, if you're trying to set up a routine, make sure you know which isotopes have interferences. So scandium, aluminum, niobium tend to have interferences. We need to do some sort of normalization to correct our data. And then the data reduction can be quite arduous. So it's typically done in iLight. We have an in-house data reduction routine, which I guess is currently in Excel, but maybe Kurt will switch over to MATLAB again. And it's much, it's quite easy to remove any spikes where you're seeing inclusions and that type of thing. Okay, so one of the things that we do to our trace and rare, or to our rare earth element data is just like we did for hafnium. Remember, we normalized to Chur there, chondrite normalized. We basically do the same thing for trace elements. And so this is purely a function. We do this because of the Otto-Harkins effects. So elements with even atomic numbers are more abundant in the universe. And so you get this, spiky pattern in rare earth element space, which is pretty hard to interpret if you're looking at multiple populations. So all you do is you go in and normalize it. That process is pretty easy. You just divide it by known chondrite compositions, and you get something that looks much smoother. So most rare earth element data that's published is normalized. So if you do produce this type of data, that's probably a good thing to do. Okay, so you've come to our lab or you've gone to another lab and you've produced your own trace element data. What in the world can you do with it? And this is kind of what I was saying. There's so many uses for trace element data, and I think we're really kind of at the tip of the zircon for this one. There's lots more material, lots of different applications that we can start exploring. So the first thing that you can do is, simply discrimination diagrams. You've gone out, you've taken a sandstone, you've analyzed the trace element compositions, and you want to say, did these come from granitoids or from basalts, some weirdo basalts that were producing zircon, or metamorphic rocks? What was the host rock of this? So discrimination diagrams are a big one, and you can use it to get at rock type or tectonic setting. It turns out that if you have appropriate exchange partition coefficients, you can start to reconstruct whole rock compositions. And that might be really important if you're in an area where you're trying to get back at whole rock values for some reason. We'll go through a couple of techniques that involve that. I mentioned that the exchange of titanium into the crystal lattice is a temperature dependent process. So it turns out that we have a thermometer with zircon, which is kind of cool. Can do all sorts of stuff, looking at cogenetic phases, what's crystallizing. If monazite's crystallizing, that turns out to have a big effect on your thorium uranium concentrations. And so you can start to get at what a metamorphic zircon is versus what a igneous zircon looks like. And then there's all sorts of diffusion studies, which I'm gonna stay away from today. Okay, so going back, giving Belousova even some more love. So this was her paper, 2002. She went in, analyzed all these different zircons from different types of rocks around the world, and found these kind of characteristic discrimination plots that could be used to differentiate, say, granitoids from a syenite. And some of these work really well, and other ones don't work so well. But there's a bunch of different studies that have come out since that have similar discrimination diagrams. So finding one that works for your sample set can be important. So they've also been used to tell something about the character of the parent melt, whether it was metaluminous or paraluminous. So this is primarily done based on aluminum content. This is a pretty well-cited study from Trail et al. 2017. They've been used to tell something about tectonic setting. This is a pretty cool study by Grimes et al. 2015, where they basically break out zircon type in scandium ytterbium and niobium ytterbium space, and showed that you can break out continental arc versus mid-ocean ridge versus OI type zircons. And this is basically controlled by the impact of fractionation depending on what phases you're crystallizing. So if you're crystallizing titanite, amphibole, or zircon. So here's an example that was produced in our lab pretty early on, I think this was one of George's early data sets. And so NIST and 91500 here are our standards. These little white dashed lines are the known compositions. So we're doing a pretty good job of reconstructing those. And then we have a tonalite, a diorite, and a gabbro. And so we can differentiate them based, purely on their rare earth element spectra, or we can start looking at them in different cross-plot spaces. So for example, their cerium versus europium anomaly, or niobium versus tantalum. And you start to get some separation here. And this is really compelling if you have zircons in a basin and you have multiple source regions that are all the same age. You could start to fingerprint those different source regions with these trace element chemistries. So once you have a trace element chemistry and a zircon, this is some really neat work that came out by Jay Chapman, where he's come up with a way to use those trace element chemistries to get back at a whole rock composition. So in this diagram on the right-hand side, these red lines are reconstructed approximate whole rock compositions. The black line is the measured whole rock composition. So these red lines are reconstructed with zircon, the black line is just measured. And so, to do this, you need to know your partition coefficients between the zircon and the melt, but he's come up with a way to estimate this in most rock types, which is pretty cool. So the reason I'm so excited about reconstructing whole rock composition is because if you can do that, then you can start to think about processes like crustal thickening, for example. So this is not work done in zircon. This is work done in whole rock samples that looks at, this is work by Perfetta et al. 2015, where they look at whole rock samples from quaternary arcs around the world, where the MOHO depth is known through tomography. And they find a strong correlation between the MOHO depth, so crustal thickness, and the median lanthanum and values for different quaternary arcs. And so they basically suggest that you can use this equation to reconstruct crustal thickness based on a whole rock lanthanum and terbium value. And this is basically controlled by the fact that garnet and amphibole really like ytterbium and yttrium. And so if you have thick crust, those two numbers go down. And so there's a strong control on MOHO depth based on, and the correlation with trace element chemistry in the whole rock samples. So here's an example where they've used this in the Coast Mountain batholith and the Sierra Nevada arc to reconstruct crustal thickness through time. Again, this is with the whole rock record. But what's come out more recently than that is using the type of exchange partition coefficients that Jay Chapman suggested. People have now done this in using the zircon record. So this is from a recent paper, Balika et al. 2020. And they reconstruct crustal thickness from 4.3 GA all the way up to the modern. And the suggestion here is that despite major changes in arc processes through time, their suggestion is that granitoids have crystallized more or less at the same depth for all of Earth history. Whether or not you agree with that, that's up to you guys. But it's kind of an interesting application using these large databases of zircon to get at long-term processes. So here's a super cool example. This one came out in Geology, I think just 2 months ago or something like that. So they take advantage of the same correlation that we talked about earlier. This is essentially Perfetta's lanthanum and terbium with crustal thickness. But they look at the europium anomaly within zircon and show that it correlates with the whole rock lanthanum and terbium ratio. And they basically attribute this to the fact that when you have thin crust, you get lots and lots of plage crystallizing. So you get a lower europium anomaly in your zircon. And so they correlate the mean europium anomaly in zircon with crustal thickness. And using this, they're able to reconstruct the crustal thickening history of Tibet from about 150 MA to modern. As Kurt points out, it falls apart in the most recent time frame in the Cenozoic. But it's kind of an interesting application of trying to get at these these processes using the zircon record. So this is kind of a cool paper, similar type of long-term evolution of crust. This is basically reconstructing, I guess, arc processes through time. So they basically identify 3 pulses of magmatism in the detrital record. And they use kind of these characteristic trace element chemistries through time to say something about what's going on. So they say that these pulses of magmatism correspond with high thorium-uranium ratios. This ratio, they say, reflects progressively more depleted heavy rare earth values through time. And that the presence of these high uranium over ytterbium values represent crustal thickening and increased fluids through time as well. Okay, so I mentioned early on that the titanium can substitute into the zircon crystal lattice. It goes into that silicon site, and it doesn't always like to go in. Its ionic radius is such that it doesn't fit well, and so that process of it being exchanged into the zircon lattice is is controlled by temperature. And so this assumes that the melt was saturated in titanium, meaning that rutile is present. But what we find is that this process is not dependent on pressure. It's really just a temperature controlled process. And so if you look at the titanium concentrations in your zircons, that tells you something about the temperature at which that melt crystallized. So here's an example of an application of this, which I thought was kind of cool. So here's their, zircon rare earth element spectra. But what they've done here is they've done this on lunar zircons. And on the left-hand side, they've basically said that anything with greater than 400 ppm of iron is an altered zircon, not reflective of the parent melt. They do that based on some values for other typical Archean zircons on Earth. So they assume that these are all reflecting parent melts generation. And they basically use the titanium concentration to reconstruct temperature of crystallization. And they suggest, based on these high temperatures that they're getting, as well as some of the rare trace and rare earth element patterns that they see, that these were lunar zircons formed from anhydrous melts. So an interesting application to kind of planetary body evolution. Okay, so I also mentioned the thorium-uranium ratio. This one's really good because even if you just come to our lab on a normal day, you're already going to get thorium and uranium concentrations. That's just something that comes out of a normal analysis with us. So even if you're not specifically targeting trace and rare earth elements, it's kind of an easy go-to proxy. And so typically these low thorium uranium, less than about 0.1, are thought to be metamorphic. Greater than about 0.3 are thought to be igneous. Again, we measure these all the time. We think this is probably controlled by things like monazite, which takes up a lot of thorium, growing, which causes zircon, a cogenetic zircon, to be depleted in thorium. But there's some other, potential mechanisms too that have been proposed to explain this type of ratio breakout. But this is a nice fingerprint for what, if you're using, say, detrital zircons and you're trying to get at, was my source region metamorphic or was it igneous? Okay, and here's an example to a detrital data set. This is kind of a nice visual graphic for us to look at. So this is in the Adriatic 4 deep, and they've got some deep water fan deposits, and they've got like 7 different sources for these fan deposits, potential sources. And so this was done in Danny Stockley's lab at University of Texas. And they're doing laser ablation split stream analysis. So they have, again, one of their tubes is going to the mass spec that's measuring age. The other tube is going to the mass spec that's measuring trace element compositions. And basically they go through all of these different proxies using thorium, uranium. Again, remember that's a proxy for metamorphic versus igneous, and the slope of their different rare earth elements to suggest that there's only one possible source and it's 300 kilometers away. And so they have to do, this long distance transport as opposed to these closer by sources that have been proposed. So an interesting application to kind of the detrital realm. So those are kind of the examples I have. I'm going to go through some best practices here in a second. But I guess my main point with these slides is just that there's a lot of potential, and some of the applications we understand really well, like thorium, uranium, although we still don't understand the mechanism, and other ones such as crustal thickness, we're just starting to explore. So this is, in my mind, a pretty obvious application of where the future of detrital zircon geochronology lies. Okay, so going to some best practices, these are things that we've talked about with every module that we've gone through. So you have to have standard bracketing. You need a lab with published methods papers. We want you to come visit the lab. We don't want you to just send us samples. We want to see your face. We want to be able to talk through the data with you. It's really challenging to convey the complexities if you're not there in person. Run lots of standards. This is, I think, especially true with trace elements where we do, you need the corrections for sure. Like hafnium, you want to make sure that you're not analyzing multiple zones. You really need CL images if you're going to do this type of analysis. It is possible to do split stream, but we would recommend that you don't. We would recommend that you do uranium lead ages first, and then go back and target some populations for trace and rare earth element chemistries. Chondrite normalize your data. That's just how it's published, and have us check your results before publishing them. And with that, I just wanted to leave up some of the Petrochron seminars or Petrochron sessions that I pulled out from this year. I'm a little biased here. I'm chairing this session and I'm presenting in one of these, so I'm a little biased in what I'm putting up here, but these were kind of the sessions that I pulled out that were relevant to kind of future of petrochronology, geochronology. So so feel free to hop on the chat box. I can go back to any of these slides. They're all available